All right, so this is a fairly straightforward problem. You just need to remember how to handle the problems like this. So whenever you're plugging in, first of all, you can just circle there your answer, what you got is for the correct answer. I allow more people into the classroom. Well, and you can feel free at any point to circle over there, A, B, C, D, or E, which one is correct. While I set up the problem real quick. All right, so we want to figure out the predicted carbon dioxide emissions for the car of this type with fuel economy of 20 miles per gallon. Now we need to read what X and Y represent because we need to know that we're plugging our X into the correct, that everything's getting plugged in correctly. But it turns out that X represents fuel efficiency in miles per gallon. So this 20 just gets plugged in right here for X. And now we can go and evaluate that if we want. So I'll just do that real quick. 7 minus 0.045 times 20 is 6.1. All right, so I now have the natural log of y hat equals 6.1. We want to get y hat by itself. So we need to raise both of these e to the power of both sides. These kind of cancel out. Y hat equals e to the 6.1 power. And our calculator can give us that answer, which is 445.857. And well, anyways, we don't really care that much about how many decimals there are because the answer is going to round to 446. So hopefully you guys were able to look at that. Oh, I see someone chatted me the answer. So that was correct. Very good. Okay, so not much to that, except we need to remember about using E. Okay, so there it is, the linear regression t-test. Remember, if it's linear regression, it's going to be t. The only thing that uses z is proportions, but everything else is going to be a t-test, or of course, if it's chi-square, it'll be a chi-square test. Okay, so this is just a random thing before we get going. The problem statement assignment is on Canvas, and this is just your reminder, your check-in to make sure that you are thinking through what question you're asking for your project, what your hypothesis is, what test you're going to use to test your hypothesis, and where you're going to collect your data. And of those four, where you collect your data is going to be the most time consuming. We already talked about that. So make sure that you're not waiting until Thursday or Friday to turn that in. Make sure you're working on that now, collecting your data, because you don't want to, and what I really don't want you to do is turn something in and then after the fact go and try and collect your data and then realize you don't have the data for what you said you're going to do. So hopefully everyone is on the ball with that, but make sure you're working on it. And this assignment specifically, if you go to the Canvas page, you can find under its own module, it's just project module. So you just go into modules, you'll find it. You can turn in this assignment. It's going to be a file upload. So if you just want to take a picture of a handwritten paragraph, or you can upload a Word document, however you choose to do it, upload something by Friday. All right, if you have more questions on that, of course, we can talk about it, but we will move ahead and talk about the linear regression t-tests. So you are well aware that a t-test is used to test hypotheses. So in general, a null hypothesis represents no change. And we're always testing the alternative, which is that there is some kind of change, some kind of deviation from the norm that maybe is a better explanation for what's going on. So in regression, the no change option is that the slope is 0. And what that means is that there is no relation between the two variables. So you have no association between them. So if you have, these two quantitative variables, the null hypothesis is that there's zero slope. and no association. And a change in one has no bearing on the value of the other. Alternative hypothesis is based on the context of the problem. Now, this is one, when it was chi-square, our alternative was basically like, well, it's not the null. If the null said it follows this distribution, our alternative is like, it doesn't follow. It doesn't, these two distributions don't match, something like that. But now we need to go back to what we were doing with our other inference test. It says, our alternative could be that our beta, remember that's a population slope, can be greater than 0, less than 0, or not equal to 0. And we'll come back to this probably, but we could have an alternative hypothesis. If the null is that there's no slope, something like that, well, the alternative could be, well, there's a positive slope. Or the alternative could be that there's a negative slope. Or maybe the alternative is just that it doesn't equal 0. And in which case, we would be using a two-tailed test because we're not sure if it's a positive or a negative slope, but we are feeling pretty strongly that it's not 0 slope. There's some kind of an association. So we have to make that decision based on the problem and the context. And so we will think through that as we go through 2 examples today. Oh yeah, this is somehow I copied that. Anyways, these are the hypotheses that we've got. So beta is equal to 0, and then you pick of these 3, beta is greater than, less than, or not equal to 0. And that's just a nice reference for you to come back to for your linear regression. Okay, the general formula for a test statistic is given like this, and you should be well aware of that by now. Now, the specific formula for a test statistic is going to be B, the sample slope that we get from our regression, minus beta, which is a parameter that we're estimating or testing. And the standard error is going to be S divided by S sub X times the square root of n minus 1. And remember, S is the standard deviation of the errors, of the, not the errors, the residuals. Okay, so pretty straightforward as far as that goes. And when I say it's straightforward, this part right here comes straight from the AP formula sheet. Okay, and I just, you know what, I will pull up the AP formula sheet because we can see that right here. If I go down to the bottom of the second page, we're looking at sampling distributions, and this is where we would use inference for slope B, and notice the beta right there for the population, but standard error for the sample statistic is right here. So I just lifted that formula straight from here and plugged it into our equation. So now we can go back and move forward. So this is always available to you. You just need to know the statistic minus the parameter divided by the standard error. And then you can substitute whatever you need. Okay, now our null hypothesis is always that beta is 0. So we're essentially doing this formula, though I would recommend writing out the minus the beta. But keep in mind, it's just going to be minus 0. So essentially, it's just B divided by the standard error, which is pretty convenient. Okay, so regarding technology, and the first part right here is related to your calculator. And let me run through all the stuff on calculator, and then I'll add something to it. Okay, so if you want to do this, and I'm sure a lot of you could figure this out on your own at this point based on everything that we've done, but you can find the linear regression t-tests. It's very straightforward if you have 2 lists of data. And there you go, you must have your data in lists, and you can select what your alternative hypothesis is going to be, and the calculator will automatically apply a 1 or 2-tailed test as appropriate. All right, to show your work, you would want to substitute the values from the calculator into the formula. So you would show your, just because you can't say, here's my answer without showing any kind of work, you want to show something. So if you had your B minus beta divided by S sub x times n minus 1, you could plug these numbers in. You know what your n is. You know what your b is. It tells you s. Now, you can also find your standard error. So you can kind of work backwards. And if you don't even plug all those numbers in, you could at the very least do something like this: b minus beta over the standard error, and just plug in what that value is. That's something. All right. So don't just put, here's my t statistic, here's my p value. Don't just put that. You want to put something else like this right here. Okay. Now, the other thing I want to mention is that it is highly, highly unlikely that you would have a problem on an AP test that requires you to use your calculator by putting in data in lists and then using your calculator's linear regression t-test. Because remember, these AP tests are designed to be taken without needing a calculator. So you can't really do a linear regression t-test without a calculator. That's not something you can do by hand. So almost certainly you'd be given a computer printout where you'll need to read through the printout, kind of find the relevant numbers and substitute those into your formula. And this is another key thing. A computer printout is going to automatically have a t and a p value there. And we'll look at that later. But those are results from a two-tailed test, all right? So if it's going to be a one-tailed test that you're going for, then you just, I say multiply the p-value by half. I could have said divide it by 2. You get the idea. Take half of the p-value when you see the computer printout, if it's a one-tailed test. Okay, we still have the same conditions for inference: linear, independent, normal, equal variance, and random. So we will see in our examples today that this doesn't really matter a whole lot, but it is important to conceptually understand this. And I can't predict exactly what elements of this are going to be the most important for you, how they might appear on a test. So just kind of be prepared for doing anything with those. Your degrees of freedom. This is something that you'll need to remember. It's n minus 2 here. Remember, we're dealing with 2 quantitative variables, not 2 samples of the same variable like we did with difference of means. This is 2 different quantitative variables, which means we need to allow for more uncertainty. If you've got a t distribution which has fatter tails, doing 1 less degree of freedom makes it a little bit wider. And this is actually more extreme than it would really be. But if this was degree of freedom equals n, this would be degree of freedom of n minus 2. A little bit fatter, more uncertainty on the tails, higher probability that it ends up in a more extreme value. So that's why we do this, because we got 2 quantitative variables, which increases the uncertainty. All right, it doesn't change it by much, but it does change it a little. Okay, so we're going to look through this example, and this is a good one because it has all of the relevant information that we need right here. We can go through this, no problem. And for the scenario here, a business analyst was interested in the relationship between a company's sales and its profits. She collected data in millions of dollars from a random sample of Fortune 500 companies and created the regression analysis and summary statistics shown. The assumptions for regression inference appeared to be satisfied. So as we're going through this, our conditions are met. So we can just put a check mark by it. So that's what I was saying a minute ago. You could very well end up in a situation like this where it says, just assume everything was fine and dandy. So move forward with your analysis. All right, so we'll run through the full process. State here is that we want to figure out what our null and alternative hypotheses are going to be. Well, we already know that the null hypothesis is that the true population slope is 0. But our alternative is that, well, what do we want to do? Does it say specifically that we're testing that we have a positive slope or a negative slope? we are comparing, and this is where it's, maybe I should do this somewhere else because we'll want to keep it around. We are comparing sales as the explanatory variable to profits. And would we predict that increase in sales is a decrease or an increase in profit? Maybe we can think of it this way. Would we expect a negative slope between these two, or would we expect a positive slope?
Positive.
Positive. Now, if what a safe thing to do with stuff like this is if you're not sure, then just we could go with B is the beta is not equal to 0. That's safe. It's conservative. It's going to give us that two-tailed p-value, and we will, which is a bigger p-value, and it's harder to reject the null that way. So we can be safer by doing that. Maybe we're convinced that this is the only alternative hypothesis we're interested in is that sales and profits are positively associated. So, you know, just for fun, let's, because it is fun, right? We're going to assume this. And remember, when we're talking about beta is greater than 0, we're talking about the slope. So here's greater than 0 would be a positive slope. 0 would be a flat line, and less than 0, this is, I know, hopefully an unnecessary review of basic algebra, but it's something different that we're talking about here compared to all of the other things. We're not talking about means or proportions, we're talking about the slope of a line. And so we kind of need to think through it that way and maybe visually process it to say, I think there's a positive association between these two, so I'm only testing that beta is greater than 0. All right, so think through every problem like this and kind of think about the fact that you're dealing with slope. All right, I will leave this other graph chart, whatever, up in the corner. My significance level here, we'll go with 0.05, not knowing any better. Plan. This has different names for it. You could look online and see a lot of people calling this different things, but it's probably acceptable to refer to this as a linear regression t-test with the assumptions having been met. Now, if this was an actual FRQ, you might want to say the assumptions for regression inference have been satisfied according to the question prompt. All right, so do, we're dealing with a t statistic, which is going to be the stat minus the parameter divided by the standard error. So now I can do a more specific one, which is B is my stat, beta is the parameter, the standard error is S divided by S sub X times the square root of n minus 1. All right, now just to kind of jump ahead, the number that we get for this down here, our standard error, it's going to be 0.0075. So you might wonder why we don't just plug in 0.0075. Well, it's better to show more of the numbers if you can. So what we're going to do is we're going to find S sub X, and N and plug those in and calculate this out more fully. So I'm going to not worry about this, though I can use it to check my numbers. And I want to find, I already know, first of all, that beta is 0. So I'll just plug that in right now. And again, you might want to follow along. This is question 30 out of your textbook. So you might want to follow along and kind of be copying down what this process looks like. B is the slope of my sample, and this is found where you find the variable right here. One of them is your y-intercept, and we don't care about that. The other one will be my slope. Now this doesn't look like much. In fact, I didn't give myself room to write with, but we might automatically have an intuition. Wow, this is less than 1/10 as far as our slope. So is that significantly different from 0? Well, we can't just look at the slope number itself and determine that it's statistically significant. So we need to actually run the test. So anyways, I got 0.0925 minus 0. And now I need to find S. And this is the only thing that's given in the printout that is just labeled as, the notation that we expect. So S equals 466.2. So I'm going to straight up plug that in right here. All right. 466.2. And then S sub X, this is where it's good to have this drawing. And I know that my sales are predicting the profits. And it doesn't, and I should maybe spend a second on this. It never tells me that sales should be the X value and profit should be the Y. But this is where you kind of have to use some intuition a little bit and just kind of think through what makes more sense to explain the other. Profit is kind of the final number you get after you take away your expenses, you think of your revenues and things like that. So profit is kind of your end number. So it makes sense for that to be the response variable, and sales are the input that kind of feed into what your profit numbers are. So we would look at our sales first of all, and then we could use that to predict what the profits would be. So if you think through it that way, sales would be the good explanatory variable. All right, so knowing that this would be X, this would be Y, I don't care about these. At least in this context, I don't care about it. What I want is the standard deviation of the sales variable, sales data. So anyways, if I look at sales, here's standard deviation. And so I want this 7,011.63. And then the other part is my square root of n minus 1. And the count is given two different places here, but I've got 79 in the 79 data points in the set. So it'll be 79 minus 1. All right, so now we can do the calculations. If we did this right, we should get 0.0075 in the denominator, and we can calculate everything out. Now I want you to plug that in your calculator, but it will equal 0.0075. All right, so once you do this and you got your essentially 0.0925 divided by 0.0075, what is the t statistic? Anyone can write it in right here at the end. Okay. Now, depending on your precision that you kept, you might get a slightly different answer from there. But as you can see, and hopefully your statistical intuition is there and you can see, wow, this is a very, very big t statistic. And whenever I calculated, I got 12.29 because I kept a little more precision, but that makes no difference at all. So this is a huge t-score. So if if you think about this in terms of the fact that you could get, assuming that the null hypothesis is true and that there's a certain deviation from that 0 that would be expected, we end up with a distribution. I'm going to draw this distribution very tight with a long tail over to the right, and that's not even long enough. So here's 0 right in the middle, and we have our standard error right here. That's a separation. So I need to go 12.3 away. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see that's not even far enough. So somewhere I'll just pretend that we went far enough. And I'm just going to say this right here is my t statistic. I'm going to get that area under the curve, which will be my p-value. And I mean, we really don't even need to run. We don't need to figure out the p-value to know that this is statistically significant, but let's go ahead and do that just for completeness, just to remind you. This is a t distribution. We're trying to find the area under the curve. So this is going to be a CDF function, and specifically it's going to be a t CDF, and I can plug in knowing that I'm going from 12.33 to positive infinity. Those are my bounds. And my degree of freedom, well, what is the degree of freedom going to be?
$77.
There it is. We had 79 for n. So degree of freedom is just going to be 79 minus 2, and therefore 77. So I can go to TCDF on my calculator, second, and variables. So that gets me to distribution. Whatever your number happens to be, mine was 12.29. It's not going to make any difference at all. The upper is 99, and degree of freedom, 77. And this number is just so small. 3.9 times 10 to the negative 20th. I don't think we've had a smaller, can't even fit the 0 on. Whatever, that's supposed to be 20 right there. I don't think we've ever had a t score, any test statistic that big with a p-value that small. So that's just obviously statistically significant. If this was a two-tailed test and we decided to run this as a one-tailed test, according to our hypothesis up there, but if this was a two-tailed test, we would need to double it, which would have no effect. We're still at, just incredibly small number, but keep in mind, if you ran this as beta not equal to 0, you'd need to double whatever answer you get. So we can leave it as is, and now we can have a conclusion. And I'm not going to write it all out completely, but I want to remind you of our template for this. So because our p-value, or the p-value is less than the significance level, and this is where you can plug in the numbers, we reject the null hypothesis. And then we could add in, there is convincing evidence that profit and sales are associated, or we could even say positively associated, because we tested that particular hypothesis. And I will pause here, and if you have any questions, please feel free to ask. All right. Assuming everyone's good with that, I will jump to the next one. And there we go. I'll go and clear all of this. Run through this problem. And this one is dealing with brain size and verbal IQ. So you'll notice on this one, they don't give us as much information. I wanted to show you this one because, and we're kind of doing this problem different from how the book would expect us to do it, but I think it's worth it to just run through the full problem. When we don't have all of the information, we can work with what we've got. And this is enough information here. In fact, all we need are these two numbers, which is, it's good to know that that's enough. So let me run through everything. We've got our null hypothesis. Actually, before I do that, I want to sketch what's going on. I don't need to sketch it, it's already there. So let me undo that. I'm going to be referring to this scatter plot. I know that brain size is the explanatory variable. The null hypothesis will be that beta is equal to 0. The alternative is that beta is, well, what do you think our alternative should be? Greater than 0, less than 0, or not equal to 0?
Greater than 0?
I think that one's fair. You could say not equal, and that's always a fallback option, like I said, is do not equal. But it's also fair to go with greater than in this case, because I think the alternative explanation would be that the bigger your brain is, the higher your verbal IQ. So I think that's a fair alternative assumption or alternative hypothesis here. So I'm going to assume that we actually have a positive association and a positive relation between those two. Significance level here can be 0.05. It does say right here, if you read through, I didn't read it for you, but it does say assumptions for inference were satisfied right here. So when I get down to the next part, I can say that I'm going to do a linear regression t-test, and assumptions for inference were satisfied. I'll just put a check mark there. Of course, like I said before, write a sentence to that effect. It says, from the question prompt, we can see that all conditions for inference were met. Okay, do. So this is same as before, stat minus parameter divided by standard error. And my specific formula is going to be b minus beta divided by s sub x times the square root of n minus 1. All right. So for my standard error, I can't do this problem the same way I did the last one, because it does not tell me s. It does not tell me s sub x. And actually it doesn't even tell me n, but I can figure that out. In fact, let's count these dots to find what n equals. So as soon as you have the sample size, go ahead and write that in. Very good. We got 21 in our sample size. And again, I think if you looked up the answer key in the back of the book for this problem, they're not expecting you to do all this, but we can, so we're going to. Oops, didn't mean to do that. So 21 is the sample size. Now that's all well and good. That's going to help us with our degrees of freedom. So what's our degrees of freedom here?
$19.
There it is. Just subtract 2. All right. So I know the b, the beta. Sorry, not beta. I know b is given right here because my y-intercept I don't care about, but the other coefficient I do. So I will go ahead and plug that in, 0.098842. Beta is 0, so it'd just be minus 0. I'll just leave it as is. Now for the rest of this, I don't know the standard deviation of the residuals. I do not know the standard deviation of the x values, of the x data. I do know the sample size, but I really can't plug stuff in the denominator. But remember, this other value right here is your standard error. In fact, it even says right there, standard error. So I'm just going to plug that in 0.0884. If you got data that looked like this is the best you can do, and this is acceptable. Okay, so pretty straightforward at this point. We get to reduce this entire complicated looking problem down to a simple division problem. Take this number and divide it by this one. So as soon as you have that number, you can write out what that t statistic is. All right, and you can keep writing out that number as far as you care to, but 1.118 is a good amount of precision. And there we go. So now if we think about the fact that our null hypothesis is that there is no slope, that beta equals 0. Now the result we got put us about right here, maybe it's a little further than I should have put it, but it doesn't matter. So this is our t statistic right here. We want to figure out what's the probability of getting that value or more extreme, and we're only doing a one-tailed test. But let's just kind of roll with that for now. So 1.118 is our lower bound, up to positive infinity is the upper bound, and we got 19 degrees of freedom. So I can figure out this p-value right here, which is the probability, the area under that part of the curve. So remember TCDF, and plug those numbers in. And as soon as you have your answer, I'll just put p-value right here. And you guys can fill in whatever that value is. Okay, so 0.1388, and just for fun, real quick, I'm going to pretend that we had this as our hypothesis. And now what we did, this is a one-tailed test, and we're done. If it was this instead, then what I would have wanted to do is double this to get, 0.278 basically. So this would be for two-tailed. Now it turns out it doesn't matter if it's one or two-tailed, because in both cases, it's above our significance level. It's greater than. So I could write something to the effect because sure, the p-value is greater than the significance level. I can't really write today. And I'd put in the numbers. We fail to reject the null hypothesis. We could say there is not convincing evidence that brain size and verbal IQ are related or positively related, however you want to say that. All right, and that's basically it. I'm pausing for just a second in case there are questions that come up. Assuming everyone kind of has the hang of it, there's no questions, here's your homework. And what I want you to focus on for this, your test isn't until Friday, but you can already start preparing because we're done learning stuff for the test. Except, like I said, as we're reviewing tomorrow, there might be little things here and there that I want to kind of make a point about. But the problems in your homework, this has kind of been true all year, but just to state it again, these go into kind of the full process for how to conduct these inference tests. And I highly recommend you go through these. There's only 5 problems, but they're very long, intense problems. So do as many as you need to until you've mastered it. And some of these ask for you to also create confidence intervals. That's good review of what we did yesterday. So go through this, but don't just call that good. I want you to also look at your Unit 9, AP Unit 9 progress check. And these are going to be the multiple choice questions that your test will be modeled on. So we're going to look at some of these types of problems tomorrow in class, but it's a good idea to go ahead and get started with that right now. If you're not in the habit of doing it, this is our last test like this. So I want you to try and ace it. So anyways, that's about it for today. If you have any questions on anything, stick around. But besides that, you can have a wonderful day, and I'll see you tomorrow.